were all wrong. That's yeah, me too.
Textbook in this class. Do you have Hyman's textbook?
So you said Dr. Simone had his baby?
I'm not sure. It's due date today, so.
That's so exciting.
This class?
Yeah.
Yeah.
Yay.
Oh, it's on the Google Drive. Yeah, you probably have it.
How are you doing, Michael?
I'm doing well. How are you?
Okay. Like I said earlier, it's Thursday, and it's even more into Thursday than the last time.
Forgot what it is.
Not because of like this thing.
Okay. So let's get started. Today, we're gonna have our homeworks for the chapter 1. So everyone got a copy of this. Most of the questions we have talked or will be talked today in the class to give you some of the example in real problem. One more.
Thank you.
2.
Thank you.
Perfect. Okay, so let's begin. So what we're going to do today is we want to continue our chain statistic courses. And some of the key things we want to talk about is, first, today we're going to give a real example. We will go through an example together on the table, on the board, to go through how does it works like in real life. In the Polymer research lab, you're going to use what we learned in the first class. The second part is where we're going to discuss a little bit more in detail how does chain statistics in real life. What we chat a few days is still like polymer chain in vacuum, it's ideal chain. So the second half of the class, we're going to talk a little bit about in real world, how does these chain looks like. So in the last class, we go through a new concept called radius of gyration. It's a parameter that we discussed about how does that can be measured by light scattering, right? So let's recap what we talked about, RG. So radius gyration is a parameter that basically tell you how big your molecular is or your chain is. It's measurable by light scattering, so you can be measured by light scattering. And this is a parameter. Is later we learn RG is actually square is just equal to 6 of h squared. This is end-to-end distance. So radius of gyration and end-to-end distance are fairly closely correlated. So if you can measure this parameter, you can back calculate that. And definition of radius gyration is somehow more related to what a real chain is, because radius gyration take consideration all the part of the chain segment into consideration. So it's average of each individual segment over the whole segment area, right? While the end-to-end distance takes more consideration in the chain ends. Together with several other parameters we learned about in previous class, we can actually get a pretty good handle now how does a chain orients, how big it is inside a polymer solution. So for the first half of the class today, I'm going to discuss an example of a graduate student. When they finish year 1, then they're excited to go to the lab. Then one of the professor who is interested to use light scattering, what the experiment will be look like. So let's use that as an example. Imagine now you made a new polymer through quickly amongst that you passed all the hurdles, there's challenges in the reaction, but now you have a polymer. You just did a GPC, you know the molecular weight. Then you're excited to see how big the chain is. And as I mentioned, what you're going to do is do a light scattering. So let's skip all the details about what the light scattering is, but in the end, let's say you now get a molecular weight by light scattering, okay? As well as you can probe the radius of gyration by light scattering as well. This is slightly different to what the molecular GPC will measure for you, which we will talk a bit more. So, and you can do a simple math. This is what example what we're going to talk about today. We're going to talk about a good example of very simple polystyrene. So example, what we're going to talk about is polystyrene in cyclohexane. At roughly 35 degrees Celsius. And now you made several different molecular weight, and you can plot the molecular weight in one axis while the other one on the other axis, right? So let's say you plot molecular weight on a log scale. Then this is another one, RG on a log scale. LGRG, then you can get a slope of it, and you can get an intercept, right? You can, for example, measure a couple points, get a relationship. This is what you would get. Let's assume.
So your y-axis is the log of RG?
Yeah.
Okay.
And you will see that because what we need to do log is now we can fit this slope. But this is just an example, okay? This is what you would be measure, and this is what you would be get. You can measure the RG, you can know the molecular weight, and you somehow find this relationship. And now you can use this information to understand how does that relate to the chain statistic. Question?
The exponent?
0.51. Yeah, this is the same example you would see in the textbook if you read the polymer physics textbook. So that's the same example. So
where do you get that number 0.51? What does that mean?
that's a slope, or that's a relationship between the RG and the M molecular weight. So if you pay close attention, if it's ideal chain, it's not a 0.51 relationship, right? Right? If it's ideal chain, it should be proportional to the molecular weight of 0.5 instead of 0.51. And this is sort of more realistic in real solution. And we will use this example just to show what we're going to chat in the rest of class.
What is the slope in this case?
This will be 0.51.
Oh. So what's the 0.25?
0.25 is pre-scaling factor. That is will be log. You can intercept here. That's a log 0.25. 0.25. Okay. Question?
Is the 0.25 specific to cyclohexane, or is it true for all polymers?
Oh, it will depend on. So this is just generalized for all the different polymer. You will get different this and different this. It is material dependent and solvent dependent and even temperature dependent. So what we can do is just to use this to understand what these parameters are. And you can know how rigid your chain is inside this particular case. Okay? So where we should start off? Question in the back? Yeah?
So
Mm-hmm.
I think what everyone is just trying to ask is there an equation that of this form that just has like what the pre-scaling factor is? Like, is the pre-scaling factor like part of
That would be
C
B.
and pin? Oh, it is B. Oh, I'm dumb. Okay, cool. Sorry.
Is it clear? I mean, if anyone don't understand this, is it confusing for you guys why we say a log scale or? Because otherwise, it's not linear. Because, let me write this for you. So log, if you take log on each side, it's again mathematics tricks. Log RG will be equals to log this giant equation, right? NW 0.25. So this, if you do the math, what it means, it's going to be log 0.25 plus 0.51 log molecular weight. Is anyone know how does this thing works out?
Is that your linear? That's your original equation. Isn't it just like?
So let me, yeah.
It's like, yeah, it makes sense, like-
Right. So I guess what confusion to some of you is why a to the power, this is exponential, right? So if you plot a versus y, if it's we use y to a power of x, so this will look like this way because it's exponential, right? So, but if we plot log y versus log x, this will be a linear. And so this is log y, log x, and slope will be a because this equation will be interchangeable to log y equals to x log a, right? Okay.
See, what I don't get is when
Mhm.
you have logs in all those equations. If you take that 10 to the power of whatever and you cancel the logs, then you'd get the radius of gyration is equal to 0.25 plus 0.51 times the molecular weight. So you get RG plus the intercept plus the molecular weight. I don't see how that's not linear.
Sorry, I'm confused. Can you repeat
I'm
it?
just thinking, that doesn't seem like a linear equation to me. It seems
Oh.
like if you were to go 10 to the power of the log and cancel out the logs, then you would have a linear.
So let me try to explain to you. So this is constant, right? Log a number is a constant, right?
Yeah.
And plus this log molecular weight is now become the x.
Yeah.
So basically it's 0.51 x is y. So if you plot this
Yeah.
y equals to a linear multiplied by x.
Yeah.
Is it getting better for everyone? It's a good warm-up. Okay? So now we understand how does this log a, because anything on the exponential you have to plot it in a log way so that they can become a linear. Okay?
What is your LC? Molecular weight by LC?
Oh, light scattering.
Okay, so when you
Oh, LS should be.
so you measure both of those simultaneously with light scattering?
You can measure RG and back calculate what the molecular weight. It's a little bit out of scope for this class, but you will learn in the next class. Basically, what light scattering can do is to help you understand what the radius gyration is. That's one parameter. I'm sure Rebecca and Michael has learned this, right? What else we can learn from light scattering?
Varial coefficient.
Second, the varial coefficient, right? And there's one more parameter. Molecular weight, right? Absolute molecular weight. That's the intercept of the zinc plot to the y, right? Good, great. So you guys will learn. They take a little bit head start, but just to say, there has many ways you can measure the molecular weight. You can measure it also by GPC. So the point of here is we're not gonna be talk too much about how these relationships, but instead we can use these two parameters now to calculate if the chain is rigid. Okay, and how can we get? Let's get the first parameter. let's get the characteristic ratio. How would you do that with the knowledge we learned here? And where the characteristic ratio, how can we calculate that? What we know is this equation. Okay, this is a no. The question is, what is the C infinity? Any idea? Advice?
Well, we know that the radius of gyration is related to n of the n distance, and we know that n of the n distance is related to rigidity factor.
Yeah, that's
So
so.
we just need to do a little algebra and rearrange those equations.
Exactly.
But
So
then we're still left with the n times L squared. So is it possible to know like what our unit length is going to be just theoretically, or do we have to measure that as well?
So in this particular case, because it's polystyrene, so we know the carbon-carbon bond length. It's about 1.53 angstrom. So that is a no. So we have to know what L is, right? L in this case is the carbon-carbon bond length. So that's about 1.53 angstrom. That's a distance.
And then to find n, you just do molecular weight divided by the molecular weight of the monomer?
Right.
Okay.
Right. So you can do that to understand what is the repeating unit, right? So let's give it a try. So why don't we use the knowledge we learned to calculate what it is? So why don't we assume, so polystyrene, what's the monomer molecular weight?
104 grams per mole per unit.
Right. Right. Pretty close. I think if we draw, this is would be the monomer, right? If you polymerize it, it will be look like this. So we can count how many carbons. So 1, 2, 3, 4, 5, 6, 7, 8. So it's C8. Then you got 5 hydrogen here, 1 here, 2 here. So C8H8. That's exactly 104. Good job. So then let's assume you have a molecular weight. Because now this is a linear relationship. You just can assume a molecular weight, then calculate what is Rg is, right? So what we're gonna do is first tell it what we guess, give it an arbitrary molecular weight that's easier to calculate. So why don't we say the molecular weight is 104 multiplied by 10 to the 5th? Well, this is roughly 10 to the 1000 Dalton or gram per mole, right? Then you can calculate what this Rg is, right? You can use the equation right there. Rg will be 0.25 multiply 1.04 10 to the 7th power of 0.51, correct? So what we did here is use the equation or what you measured for this particular polymer to understand what their radius of gyration is.
So the units of molecular weight are grams per mole. So
Yeah.
What would your units for the radius of gyration be?
So that will be angstrom,
Be in this.
right? So this is the empirical relationship. So what you measure in Rg will be angstrom in this case. Does it make sense to you?
Does it have a unit?
Right, right. So this is not exactly, it's just to tell you what the number is. It doesn't have a unit because this is an empirical relationship what the molecular weight and Rg is in this case. Okay? So I will do the math for you because this is a pretty nasty power of 0.51. You have to use a calculator to calculate that. So you will get roughly Rg is about around this number, okay? About 95 nanometer for this fairly high molecular weight. So this is about 10 millimolecular weight. So if you do chemistry, this is a fairly high molecular weight you made these material. Typically it's on thousands or tens of thousands in terms of molecular weight. So what shall we do next step? Because we assume the molecular weight, we now can get the radius of gyration. Okay. End-to-end distance. Very good. So that is roughly, how does it relate to RG? All right. It will be not 6 times, but root 6. Yeah, good. Very good, very good. So you can get what will be the end-to-end distance for this material, right? So that's what we also learned. How does end-to-end distance relate to RG? Or, for the sake of discussion, I put the bracket for the average, but you can also remove them. That's fine for now. We are not deriving the equation. End-to-end distance RG has this root 6 relationship. Okay, so what's next? So it will be root 6 multiplied by 948 angstrom. Right?
Yeah. Which is 2,322.
I didn't calculate that on my note, but let's say yes, correct. So how about next step? We are very close to characteristic ratio, right? As I mentioned here.
What does the LM stand for? The L capital M?
Where are you pointing at?
Right to the left of the equal sign of the 948 angstroms.
Oh, this is just I'm trying to tell you how big this is. This is 10 millimolecular weight. 10 to the 7th Dalton is 10 milligram per mole, right?
Yeah.
So the molecular weight we assume in this case. It's fairly high. That's what I'm trying to say. That's why the RG is relatively big, almost 100 nanometer, right? Okay, so how about this characteristic ratio, or this is a parameter that you can understand if the chain is rigid or not. Yes, great. So how about then C infinity will equal to?
It'll equal
H squared.
over n squared times L squared.
N L squared, right? Cool, good job. So what we're gonna do now is, do we know all the parameter here? We know L, right? L is the one bond, which is the distance we talk about here. And what about N? N is number of bonds, right? Which is?
Molecular weight divided by the 104 point.
Right. And multiply by 2, because in each repeating unit there's like 1 bond, 2 bond, right? Because there's 2 carbon-carbon bond inside each repeating unit.
Can we say what they said, but louder? I didn't hear what they said.
So they was talking about what number is this N is. It is molecular weight divided by monomer molecular weight. So you can get the repeating unit, right? How many repeating unit? And inside each repeating unit, there's 2 carbon-carbon bond along the backbone, correct? So this will be equals to root 6 multiplied by the same number. That will be square, right? Divided by n. N is equal to 1.4 multiplied by 10 to the power 7. That's a molecular weight, where we assume to start off, right? Divide by monomer molecular weight is 104. And multiply by 2, this is because we have 2 bonds in each polystyrene monomer.
If you were to have used the equation capital N times B squared, where you're taking the effective length,
Yeah,
would
yeah.
that
Yeah, we will also do that calculation today.
Okay.
That will calculate what the effective B is. Okay? But that's another way you think about its effective free joint chain model, right? So then L square is 1.53 square. Okay? So now it looks a little bit complicated, but you can do the math.
I don't get why we're multiplying by 2, because if I thought n was the number of repeating units, and if it was the number of repeating units, wouldn't it just be the total molecular weight divided by monomer?
So this is if you use the molecular weight divided by monomer molecular weight, it's a degree of polymerization or monomer unit, right? Each monomer you have, if you look at this is a monomer, we counted.
I thought it would just be the number of monomers.
No, it's actually, because we are using Cl square, L is just a carbon-carbon bond. So we need to count how many carbon-carbon bonds along the backbone. Does it make sense to you?
Yeah, I mean, I get why we're doing L squared.
Right.
Or is it? I just don't. I just still think that if n was the number of repeating. Wait, so n.
There is two ways we throughout the early class courses we talk about two models we can describe a chain. So let me try to use this empty space, right? So if you have a chain, you can describe h square where we see infinity and L square. So this will be characteristic ratio, number of bonds and individual bond, right?
So n is the number of bonds. I thought it was the number of repeating units.
No. So you have another way to describe mb square. In this way, this is degree of polymerization, and that's called effectively, each monomer length. And in this case, we just assume you have another chain model that has a number of segments, each segment of B, but this follows free joint chain model that will give the same length. Okay?
So why is
Let's have this question answer first, then I'll get right back to you.
So if you had 3 carbon-carbon bonds in your
Repeating unit?
yeah, you would multiply by 3
Yes.
for little n, but
Yeah.
big N would be
The same. N is degree of polymerization.
So if you're doing something like polycarbon, you'd have like 14 or something. Like
Yeah.
or something that
Yeah. But we won't test that. I think that will be too much. Anthony, what's your question?
never mind.
Okay. No? Okay, good. All right. If you do all the math, and I did it for you, if you calculate everything, well, this will be around 11.5. So what does this mean is we have a characteristic ratio to describe the polystyrene in cyclohexane is quite rigid, definitely on the rigid side. And once we know this, if I recall, what I like to call this is, give it a nickname, not call it. Have a nickname, we call it chain rigidity factor. So C infinity is directly proportional to how rigid your backbone is, right? And we can also calculate out another parameter. If we know C infinity, we can get this persistence length for your polymer. Persistence length is, can someone help me? What is that?
Well, that's if that's much larger than 1.
C. Oh, sorry. Not this should be LP. Right? So what does this equation tell you? LP is proportional to characteristic ratio divided by half multiplied by monomer bond. And if we do, this is a 15.5 divided by 2 multiplied by 1.53, and you can get what the persistence length is. So this is about 8.8 angstrom. So the physical meaning we discussed it in the class. What does this mean is after about 8.8 angstrom, your chain could bend over 90 degrees. So your chain is relatively short-ranged, and this is about just above 6 bond or 7, a little bit less than 6 bond. Your chain can fold back to the 90 degree. And there's another parameter, LK, or cone length, which is another definition with 2LP, right? So this is just C infinity, L. This is roughly twice of that, so 17.6 angstrom. So in other words, it takes about 11.5 monomer or chain carbon-carbon bond, then your chain can fold it back to 180 degree. Okay, so if I draw a polystyrene, this may be easier this way. It's 1, 2, 3, 4, 5, 6. After about 6 bond, it changes bend to 90 degrees. So that's what you can learn from this type of experiment to measure. Just to do a very simple, measure the molecular weight using a GPC in your lab and do a light scattering to measure what the radius gyration for different molecular weight. And typically, why we do several data spots is because you need to get relative statistics. If you only measure 3, 4 data points, your curve tend to be off. So you kind of measure a couple points and then get this generalized relationship. Okay? Okay, great. So there's one more parameter we have to talk about.
Does C infinity have units?
No, C infinity is just characteristic ratio. It does not have a unit. So now come back to this. What we can also understand is what is effectively your chain effective monomer length is. So in this way, we can calculate what the B is, right? Someone asked about what is this B value is. So let's use this area to understand what is B is. So we talked about in the previous class, in this equation, we eliminate the C infinity or characteristic ratio in the second expression. So in this bottom expression, we don't have a characteristic ratio there. It's actually was rolled into this B value. Okay, the physical meaning of MB squared is now we know what the degree of permutation. We don't need to consider how many carbon-carbon bonds inside each monomer, right? In this case, some of you has maybe asked the question why we need to 2 multiplied by n to get number of bonds, right? There's another way to describe this is you don't need to do this. You just calculate how big is the degree of permutation and what's effective length of that. So the answer is B. We know what is n, right? We can calculate what is B is. N is degree of permutation. That's 10 to the 5s. And you know what the h square is, right? H square is the same value here, and you can calculate B. B will be n divided by h square. And I'll give you the answer for that. This is about 7.3 angstrom. So B, in other words, if you want to describe the same polystyrene chain, if you look at the number here, each bond, we talk about that, right? Each bond is about 1.53 angstrom. So this distance is 1.53. And if you pull, let's assume you pull them straight, you have 2 of them, so at most they're about 3 angstrom, right? Between these 2 points. But if you want, there's 2 ways. The other way you can describe is each bond is about twice the length, because we just calculate B would be equals to 7.3 angstrom. So B will be longer, but now it's a free joint chain model, can describe the same model with n number n there. Okay. So you can have n segment of this, describe the same end-to-end distance, use the top and bottom. So this will be, and in the bottom, you can imagine it's just one longer segment, but n amount of the chain bonds. Okay, it's called effectively free joint chain model to describe. If I put the dot close in the solution you measured, it could be the top or could be the bottom. They will give you the same results. So any question regarding the example I gave, how we can use very simple equations to understand how does your chain behave inside the solution? Is it rigid or is it soft? And how rigid it is, we can calculate from the C infinity factor. With that, I'll give you 5 minutes again to digest what we discussed. Then in the next 20 minutes, next half, I will talk about one more parameters, that the real chain model and a concept called scale, and how does the scale matters in the case we discussed here. Okay? And if you have questions regarding what we talked about, feel free to come to me.
For tests, are we going to be given the equations, or do we need to memorize the equations?
I'm very nice, so I will give you an equation cheat sheet at the end of the test where I describe these.
Do you know when about the first test is going to be? Did you say that already? I don't know.
I'm trying to get it in the middle of the second chapter, so it will be mid-October, where we're gonna have a test about the first chapter, chain statistics. So we will have. It's gonna be short. It's not gonna be a super lengthy test. It takes like 2 hours or so.
Okay.
More like it's a take-home exam.
Is there
So
a chance it won't be the week after fall break?
when is the fall break?
It's the 11th and 12th we have off, so 11th, 12th, 13th, and 14th. We start back on the 15th.
Okay. Can someone just send an email to me, make sure I'll check it out and plan the experiment?
I think we have stuff in every single class the week after, or tests.
Okay.
Every single other class, but I mean it's okay. It's grad school if you want to do that to us. But if you don't want to do it that week, it would be awesome if it wasn't that week. But
Okay. So let me mention to you guys about the progress about this class. So we're gonna have one more lecture next Tuesday about statistic of chain model. So by saying chain statistics, all the equation you saw these days always have a bracket on left and right side. That means we need to consider every possible chain configuration in every job. Then if you take that away, it's like use a camera to take a picture of a movie. It could be one frame of the movie, could be different from that. So we will talk about probability of the chain, how the chain end will be distributed over the time. So there will be one more class next Tuesday. Then we will finish chapter 1 of this course, or 1/3 of the class is finished. Then second part will start on polymer solution. We'll talk about the mixing or demixing. We talk about some of the new concepts about Flory-Huggins parameter. As long as everyone is comfortable, I think we can. I'll offer some of the option for the final the test for this chapter. What we can do is next Thursday would be one of the option. Next week Thursday, because we already finished.
Not next Thursday, but the next 2 weeks.
Today is Thursday, right?
2 weeks from today.
No, 1 week from today.
Yeah.
That's
Like
one
the first
option.
test?
Definitely not that. I don't like that.
No.
Okay. Okay. Good.
How about
Good.
2 weeks from today?
That would be okay.
October 4th?
Let's go, team.
But then the next
I could
week.
do
you
that.
say the
I could
exam
do
is a
the
take-home exam?
second.
And I think that will what I'm trying to do. I think that's fine.
As long as the exams
Or-
are not on the same day.
hmm
It's a take-home
Same week is
test?
fine.
Yeah, that's what he just said.
Oh.
Oh, well that changes everything. But
Okay.
So when you give us the test, and then how long do we have to complete it?
So, two way we can do it. We can do a class exam, but I'll have a student to sit here. You can have 2 hours to do the exam for that chapter exam, or we can just have it take home if that's easier for everyone.
We
Yeah.
have the same
Yeah,
exam.
Yeah,
Very good.
yeah. But the final exam will be very comprehensive. So we will have two sort of smaller exams for each chapter. So chapter 1, which we're going to finish in September, will be one test. October will be one test. Then November, for the last chapter I'm going to cover, will not have test, but it will be rolled into the final comprehensive closed book test. And, that will be very, very important. And what you have been tested before will be sort of being reflected again in the last one.
That's good.
Okay?
Right, everyone?
Oh,
Yeah, yeah, yeah,
So wait, so you give it to us, and
yeah.
then how long, like when do we have to turn it in?
Overnight.
Just the next day?
Yeah.
Oh, well then who cares? Well, as long as it's not due like the day of one of our tests, it could be like outside.
Yeah.
Then it's
Yeah.
fine. Yeah, so
The test. I will finish the test by next Thursday. Then, how about we do it next Thursday for the same day as like McCormick class. Then after his test, we can finish another test. So.
Like if you would assign it to us on Thursday, October 4th, and we'd have to have it back to you on the 5th.
Yeah. Does that work?
That sounds good.
Wait,
Yeah.
doesn't his exams take like 6 hours? McCormick's
Yeah.
exams? Have any time?
6 hours.
Well, I mean, we'll
No,
have his
it's
exam
more
at
like
5:30.
2 to 3
We have 12 hours.
What could we have
based
till
on
like
undergrad.
the night of the 5th instead of the morning of the 5th?
Yeah, because then we could spend.
Because that's Friday.
No, by the noon. Let's see. I seal the deal by the noon. So I'll hand out the test
By
on the
noon?
noon of on the class of that Thursday.
Okay.
Then the next noon by 12. Give it back to me. I'll rate that course.
Finish McCormick's exam and then go straight
It's
into
grad school. It's fine. We can do
Yeah. Okay.
How long do you think it'll take?
To be honest, within 1 hour, if everyone is happy,
Fine. Yeah,
you will be fine.
we could wake up in the morning and do it.
How similar is it going to be to the homework? Is the homework
Yeah, quite different.
like difficulty level?
It will be more comprehensive.
Okay.
Because the homework is more or less let's recap what teached in the class, and we understand some of the key concepts.
Okay.
Okay. So why don't we get back to the track? I think everyone is happy with the test date. I mean
Tuesday before fall break.
We already got it all.
we already sorted it out, so it's too late for the
It took us
question.
that long to get to that point, so let's.
So then the key thing is homework is important for you to understand what we teached. And I put the due date for the homework is the next week of this class. So please make sure you give it back to me before the time. Okay? Okay, great. So any particular question you guys had regarding the chapter 1? Chapter 1 is like a slow start for the polymer physics. Very simple concepts.
By chapter 1, you mean chapter 6?
Yeah.
Okay.
Chapter 6 on the book, but
I was like I did not read chapter 1.
right. No, read it. Actually, you want to read the book because book is very well written. I'm trying to just follow the book to explain to you the idea and concept. So right now, everyone get a good picture of how we can use the scattering techniques, use the real-world techniques to understand how rigid your chain, how soft your chain is, right? So what we're going to do next is now talk a little bit more about these chain models, what their limitations are, what are not their limitations. And that's so we always talk about the chain, and someone might confuse that, how does it relate to the real chain? Because in the chain model, we discuss a free joint chain, free rotation, or rotation hindered chain. Is all about an ideal chain. It doesn't have interaction with its surrounding medium, right? So it's a chain floating in the vacuum sort of concept. So once the chain is inside the medium, how does it will affect you? And is there another factor going to affect your chain conformation? And if someone paid attention to what we wrote in the equation, okay, so we had Rg will be equals to 0.25 multiplied by molecular weight 0.51. So anyone kind of curious what does this means and how does it affect relate to the real chain model?
I'm very curious.
Yeah. What if this is a 0.1? What if 0.2? Or what if this is 1?
Well, if it's 1, it would just be.
Oh, does that mean the stiffness of it?
We will get there very
Did you
soon.
say that was the same as the slope, the 0.51?
Yeah, that's the slope of the plot we plotted, but it's in the exponential factor. So this all these free joint chain was basically invented in the early 1940s or 1950s by a very famous Polymer physicist called P.J. Flory. So he got a lot of fame. He started in Cornell, then moved in Stanford, and he developed all these parameters. And later in the next chapter, you will learn. He also talked about Flory-Huggins parameter. Flory is basically named after him, together with another scientist. So later on, there's another genius. He has a lot of interesting story. His name is Dijen. He actually is a friend. He actually is a friend, French. So what he did is he later developed some of the new concept into the polymer chain. So if you look at this particular equation, you will realize while you do all kind of measurement, it seems you only need 2 parameters to tell a story about your chain. What is this prefactor and these? Then you can later on derive what is your chain rigidity, C infinity, etc. Right? So apparently these two are very critical in terms of understand how big your chain is. And he is so smart that he mentioned we don't need to worry about details about what polystyrene or polyethylene. Let's just consider something called a scale or a scale factor. How does one physics term could be scale or depend on the second one? So in other words, if you can understand how does this Rg depend on molecular weight, and this let's use an easy to pronounce term alpha. If you know what alpha is, you can see how they would scale to each other, right? So if alpha is large, let's say your Rg will raise rapidly versus molecular weight because it has more strong dependence on the molecular weight, right? And if anyone can help me, what the chain model we always talk about is Rg will be equals to root 6 C infinity and L square, right? That's That's the equation we always talk about in this class. Rg dependent on this. And we know the top one can also be expressed as nBL squared. So for the chain model we talk about, if you check closely, it also has a built-in relationship between Rg and molecular weight. And it scales such that Rg will scale with n power of half. The rest are just some constant in front of it, right? Or n, basically, if you multiply by molecular weight, you can get is n power of 0.5. So what does this mean is in the free joint chain or free rotation chain model, or even hindered rotation chain model, your Rg is always proportional to molecular weight power of 0.5 or 1.5. Well, apparently the particular polymer they measured was not in most ideal case, right? It's a little bit bigger than 0.5. Well, this person, Dijin, he found many more than that. There's all kind of relationship between Rg and M. It can be more strongly dependent or no dependent at all. Okay, let's give it two cases. What he summarized is in the real chain model, where we talk about in several other cases, there's a theta solvent, which is basically can represent you what is a free joint chain model is, right? Or in the melt case, where your Rg will be proportional to molecular weight power of 0.5. There's two special cases, but in real solvent, you have to consider self-avoiding walk. So it's a term means your chain cannot occupy the same space twice. So as you can imagine, this Rg will proportional to n something alpha, but alpha will be larger than 0.5 for sure for good solvent. Right? So that's a case if it's a good solvent, you can see it will be has a much stronger dependence on M. And we won't discuss in more detail. However, we will learn that from the next chapter. It's actually power of 3/5 for the good solvent. So in other words, in the good solvent system, your chain will expand faster depending on the molecular weight. And if someone recall, at the beginning of the lecture, we also talk about how does, in the poor solvent, how does that relate to what the Rg depends on the molecular weight, right? So that will be lower than that. So this person basically used a very simple concept. We now can summarize this to here. If this, we can call it bad solvent. The relationship between Rg and M, if alpha equals to a half, that's called theta solvent. If alpha is 5/5, it is a good solvent. So these three are the conditions you can rely on to eyeball and understand the general relationship between the bad theta and good solvent. And alpha is always an exponential. It tells you how strongly they depend on the molecular weight. Okay? So this is an example that he actually famous enough. He got a Nobel Prize in the polymer physics in the early 90s. I don't remember the exact date, but this is rather simple concept because you don't need to worry about all the numbers or the prefactors or what is this value. You can directly use a simple scaling concept to understand that. So with that, So there's another concept we can talk about is how to consider. I will start talk about a little bit about the topic that we will discuss in the next class, because now the scaling factor is finished. Well, we can just give a little bit early start about next lecture. So what we talk about in today's lecture is about an example how we can measure the radius, gyration, molecular weight to understand your chain is rigid or not, and you can get the characteristic ratio and etc. Then later on, we talk about a simple concept about scaling factor that you can summarize they get solved or not. So for the next about 20 minutes or so, I will start discuss a little bit about the next lecture. So what is about the next lecture? We will start to focus on the distribution of end-to-end distance. If you recall, what we started was talking about this chain, right? It's maybe too much. A random chain, okay? And we talk about end-to-end distance, h from one end to end. And throughout the discussion, we always say an average of h will be 0, right? Average of end-to-end distance is not 0. But for example, from this drawing, you can clearly see this is not 0. And the reason you see in the board this is not 0 because it's only represent a specific moment in the lifetime of this polymer chain. If in solution the chain will move around, then the average of that will cancel each other. So we kind of omitted a very important problem is, what about if we can free the chain in any given moment? What will it look like? And I can give you a few more fun examples of that. So what that will be is a distribution, a concept of probability. Okay, it's slightly different with this, but it will give you understanding what I mean by statistics. So if we take away h, this will not be 0 at a specific point. Right? Because if you frozen time, it will not be it. So what we're trying to understand is now, can we use statistics to understand the chain? So we're going to cover a little bit about statistics of the polymer chain. Okay? So what we're going to do now is to consider some of the simple model. So I'm going to start talk about a very interesting model I like to discuss. It's called random walk. So this is a concept that people usually use to understand the statistics of polymer chain. So what does a random walk mean? So now let's consider the idea that we now have an axis or a tile that it's just one-dimensional, either left or right, like me standing in front of this tray. Imagine I cannot walk this way, but only either left or right hand. So what if I say I have 50 probability to make a left and 50 probability to make a right? Okay, so let's count in one step. So let's call it 0. If I make a left, I call it a -1. If I take 2 steps, I call it -2. And if I go the other way, I can have +1 and 2. If I just take one step, if its chance is half-half, it's basically say I have equal probability on either way, right? So if you consider that, I will have I will be able to mark it as a possible chance that I will be show up on chance to show up on -1 is 1. Chance to show up to +1 is 1, because it's easy just to write it as 1. Okay, so now let's consider the example. I'm going to take a second step. After this, what's the probability where I will be ended up? If I start again from 0, now I can move twice. Now I could move right 2 times, right? That's one possibility. Or I can move left twice, or I can move once to the left, and next step take to the right to back to where I start off. Now, if you count all the probability, then it's interesting enough. You will see where I have one occasion that I will ended up at -2, right? So let me draw. This is sort of a table. So if I take 2 steps, what the chances I ended up at -1? Is there any chance I can end up in -1 if I move twice? No, right? So, because whenever I take 1 step, I will have half a chance. But if I move twice, I don't have a chance to be there. I have 2 possibilities to be back at 1. I can either move left first, then move right, or move right first, then move to the left. I have 0 chance to be at 1. Then how about 2? 1 possibility, right? So you can do now do the probability by using this chart. So you can add everything together. There's a total of how many chances you can be, or how many randomness you can be. It's 4, right? Because I have 1 at 0 and 1 at 2 at 0 at 1. So there's 4 different ways I can be ended up in this case. So then the probability I end up in the middle is actually 50%, pretty high, while I ended up in the -2 is about 25%, right? So I won't do it one more time. How about I make 3 steps? What I could be ended up, and you will soon see why I start doing this. Total possibility. What about I move 3 times?
It's a lot of difference.
A lot of difference, right? Let's start with a simple case. If I move, it will be -3, right? If I take 3 steps all in one direction, I can be ended up -3, right? There's an equal probability I will take 3 steps in one direction.
0.
Where?
-2 and 2.
Here is 0. How about there?
0.
No chance?
No chance.
Really?
Calling it. No chance.
How about here?
3.
3. You guys are really good. How about here?
1, 2, 3, 1. Yeah, there's 0.
0.
It's 0, right? There's no way you can come back in 3 steps. No matter if you take a right, take a left, then you have to make 1 more step. So you cannot be where you're starting off. How about 1? Okay, you guys are very good. It takes like literally 5 seconds. Can we do it one more challenge, okay? How about 4? One more challenge.
1.
So
4, 0. 6. 0. 1.
Can someone teach me the trick? You guys calculate so fast.
It's like a Blaze triangle.
The trick is you can add the triangles down. So if 4 is actually equal to these and 0 is equal to, because all you need to count is what's the probability from the last step where it's coming from. Then you can add it up, right? How about total probability? How about here? If you ever add everything up, it should be 16, right? This should be 8. So we don't need to go through everything, but you got the idea that if we can continue the class, do it, I think we can go all the way down to 100 steps, but we don't need to. Let's call it, and we can take an n step that you will have a distribution, right? So in the end, this is a funny professor where he will be ended up, if you take long enough steps, it will be a distribution, right? Correct? So if you count long enough where you ended up will be dependent on where 0 is where you start off. So you will have a high probability where you start off. Because the probability of this is, you can use 6 divided by 16. It's high chance you will be ended up in the middle. Okay? So now, why we do this? Because it will be useful to us to understand what the probability of your polymer chain is ends. So I want to ask you what the generalized possibility.
But you also have, I don't know, like you don't just have left and right. You have an infinite number.
Right. Right. If it's in 3D places, it will be slightly more complicated. We can help us to understand what your chain will be like. Let's say it's just a 2D chain, and if you count along, if the segment can be either left and right. So imagine this would be the chain, and you kind of confine it in the 2D space, how it will be look like. And once we understand in the 2D space, we can expand to 3D. Okay?
So you just do 0.5 raised to the n, which would be the limit as n goes to infinity. So you'd get that the ACH value approaches 0 as n approaches infinity?
That will be too complicated in that case. That will be the probability for all the, how can I say that? For the longest chance if you keep taking one direction all the time. Right?
Okay.
Right? That's the probability of reaching either or the positive or the negative. Yeah? Question?
I was going to say, this kind of reminds me of like the electron slit experiment, like where you're testing for diffraction.
Uh-huh.
So like if you have 2 slits and you're shooting an electron gun like through the slits,
Okay.
the probability that it is going to go through one or the other is going to be a combination of the two. So it'll appear as like a wave where like it'll be
Right.
slits.
Yeah.
If it went through one or the other.
Yeah, it's an interesting idea to bring up or convolute this to the interference pattern, but it's a possibility to think that way. Now, what I'm trying to ask you guys is, what's the possibility of you think your chain reaches an arbitrary number in x step? So let's say I want to reach an arbitrary number, any number here, we just call it x here, okay? Somewhere it's this in n step, okay? So imagine this is will be the 4, 5, all the way to x. This will be all the way to the low. How about this tiny box where they will intercept? What's the possibility? It's relatively complicated, right? Because if you take 2 steps, in the 2 step, the chances of you ended up in this block is 1 divided by 4. The total possibility is 4, right? If you take this step, it will be into, if you ended up number 2 in 3 steps is 0. How about I just ask you a general equation? What if I say we're going to take n step? Of course, n will be bigger than x. What's the possibility I ended up in that box? Let's first count how many total possibility. If you take n step, 2 to the power of n, right? So all we need to do is just count. Let's do a task. Is count chances of me, let's call it, end up in box X after n step. So the total possibility is 2 to the power of n, right? You would be ended up so many possibility. So how we get this? If we count, if we take one step, we have 2 to the power of 1. So in the end, you have two possibility. If take 2 steps, you will have 2 to the power of 2. You will have total of 4 possibility, right? 3 step, 2 to the power of 3, and then etc. So if I take n step, I will have the possibility of this, right? Not a possibility. Total n situation. So I could be ended up with totally this amount of chances, right? So now the question is, I need to know how many ways I can reach here. Then I just divide how many chances I reach here by total number of possibility. For example, after 3 steps, I hit number 1 is 3 divided by 8 is about 37.5 chances I ended up in this, right? There's no chance I will end up here. So generally, we just need to know the number here in this block. Then we can use that number to divide by 2 to the power of n. We know the probability I will be there. How can we count that? Is there any rationale that
2n plus 1?
Say that again? So what?
2n plus 1?
2m plus 1?
No, like
2m
plus 1.
2 multiplied by m plus 1? So we don't have n, right? So then this, we're just going to be asked what's the chance we in the x box. So let's try to find any possibility or ways you can be ended up there. So I can tell you this probably is not right, right? So now I like to think backwards. You know, the idea of we talk about is think backwards. So what you can think about where I ended up x is if I need to reach this step x, what matters in the step before x, I need to be at least here or here, right? So that one less step, I need to be next to it, so I can take one more step to reach it here. Correct? Does it make sense? For example, if I want to end up at number 1 in 3 steps, in 2 steps, I at least to be at neighbor. So I can walk to the step of, I can end up in the number -2 or -1. From -2, take a positive step, or at 0, take a negative step. Then you can walk backwards to see what's the possibility of you can be ended up there. So,
2 to the n
yeah?
minus 1?
Huh?
2 to the n minus 1?
2 to the n minus 1. So let's try. It's probably not right, but let's see. So if that's the case, then it's always, probability is always 50%, right? If that's the case, right? So in the statistics, have you guys learned something looks like, what does this mean? What does this, is there any meaning to that?
The sum of
Uh-huh.
n plus every number
Smaller.
zero that's smaller.
Yeah. So what does this means is we can do it this way. Let's say you got the 3 different color, you got n different color balls in the basket. How many ways you can take them and align them, right? You can take the first ball out. You have n ball in the basket. So you have n different way you want to take number 1. Let's give it an example for this. Let me explain. So the question let me ask is, if we have A, B, C, D, if we want to align them, how many chances it would be? Would be a perfect question for that. It will be 3 escalate mark, which means will be equals to 24 different arrangement, right? How we get there? Because if you want to arrange 4 numbers, the first number you can pick any of them, right? You have 4 different possibilities for the first one, so you can pick either A or B or C or D. Once you take one number out, the rest only have 3, so you can arrange. Let's say we take A out, then U, B, C, D can be arranged. Then you can multiply by 3. So there's so many chances you can arrange all these numbers. Same concept works out here. So the probability is or this particular number x will be equals to x, escalate mark. Oh, sorry, this should be n. And I'll explain why is this funky equation. And I'll explain why is this funky equation for this number, particular number. So we know this is going to be a number, right? So let's say to reach x, we know how many positive steps we need to take after n step. And we know how many negative steps we need to take, right? Total positive number will be m plus x divided by 2. Total negative step we need to take to reach x. So what does this mean? We want to take 3 steps to reach 1. It's possible, right? I want to make sure I'm pointing at something is possible. So take 3 steps to reach number 1. That means we total need to walk positive direction for 3 plus 1 divided by 2 is 2 times. 3 minus 1 divided by 2 is 1. So as long as you take 2 steps positive, 1 step negative, you're always going to be ended up 1. It doesn't matter if you take positive first or negative first, right? Same for here. So this is basically the positive walk. This is a negative walk. And that's the total number of different walks out of them. right? So that would be the possible way you can reach to that. It's a generalized equation. Great. And now we can calculate what's the probability of where you ended up after n step if I just are working one-dimensional linear chain. So the probability will be so the probability, let's call it probability of taking n step, which I will end up at position x, will be equals to, so that's the total number of different possible ways multiplied by this equation. This would be the possible ways where I will be ended up at walking x n steps, and I can be ended up at x. So, any question regarding this particular question? Because this will be useful, because this is only 2D, two-dimensional. I only need to go left and right. Consider my case is a walk, either positively or negatively. And there will be another case is more complicated in 3 dimension. I not only have a positive and negative, but now I can walk in 3-dimensional space. In real world, there's a meaning for that. People call it a random flight. So if I'm airplane, now I'm in 3-dimensional space where I can go up and down, left and right, or positive, forward and backwards. That sort of mimic a polymer chain in 3D, where I start from where my chain is. If I take one segment, could be any directional, where I would be ended up after I consider bond 1, and taking second bond, which could be all the possible ways I would take. And you can ask the same question for polymer chain is after n bond, after I'm counting n bond, where I am now, right? So if you expand 3-way, it's basically another way you can think about polymer chain configuration from the initial, where the chain starts to where the last bond ends. That's basically same concept right here. Well, in this case, it's basically one-dimensional. It's only left and right, and you just count after n step where I could be. So if the probability I already drew it once, but you will see that after many steps, the chances that I will be closer to where I start off is high, where I can be very far away is off, right? So probability is useful, and we will see next class. You can use the probability to calculate end-to-end distance. If you average all the probability out, that's your average the end-to-end distance. So this will conclude this class where, again, I want to mention we start with several simple math problems to convince you how you can easily use some light scattering technique to understand chain statistics. And for the second part, we had a little bit of head start, talk about statistics, how random work works out, and how you can that to understand statistical aspect of the polymer chain. Okay?